Hi everyone, and welcome. My name is Mike Howard. I'm the product manager for Oculus Avatars. So 2 years ago, my colleague Will and I got up on stage at Oculus Connect 3, and we talked about the work we were doing with Oculus Avatars and maximizing social presence. We've certainly learned a lot about avatars since that talk, and our avatars have come a long way, as you might have seen earlier today in the keynote. So today, I'm delighted to present part 2 of our adventure in maximizing social presence. For those of you who missed part 1, 2.5 years ago, when we were developing the Oculus Touch hand controllers, we realized that the high tracked fidelity and positional tracking accuracy of having hands in social VR experiences was a game changer for those experiences. Suddenly, you were able to detect and understand the nuance of body language as communicated by the head and hands, even if you were just rendering a simple avatar form like what you can see here in Toybox. We realized that people were capable of recognizing shrugging, body gestures like having their hands on their hips or their arms crossed, even so far that in certain research sessions, someone who was outside of the session could recognize her husband just based on the way that he moved, when he was just represented by a blue head and 2 blue hands, even though she couldn't hear him. She recognized the way that he shrugged, which is a weird thing to recognize about your husband, but I'll go with it. So we'd stumbled upon the first beginnings of a really much more enhanced version of social presence, which is that sensation that you're sharing a space with someone else who is really there. And this is something that is really accentuated by everything that VR can bring, like the higher tracked fidelity of where your head and hands are, the sense of immersion, self-presence, and now co-presence or social presence. And this really led to the formation of Oculus Avatars. On one hand, we wanted to give users a very comfortable and personalized variant of their virtual self to take across multiple VR experiences. And for developers, we really wanted to enable people to rapidly deploy social presence and keep up with everything that we were doing to try and advance the art of the avatar's social presence. So today, the SDK is used in over 100 apps across Unity, Unreal Engine, PC, and Android. And it's flexible, ranging from people who just use the SDK to pull in the hands for a first-person experience, all the way up to networked multiplayer titles, some of which you can see here. There are 3 ways that the Avatars team really thinks about helping developers build great social VR experiences. First, there's our core product, which is the Avatars SDK. And this is a set of integrations into game engines, sample code, documentation, things that help people easily drop an avatar straight into an experience and hook it up to be social. Then there are the advances that we're working on in simulation and avatar fidelity to make the social experience richer, things like the behavioral animation that we'll talk about later today. And finally, there's the platform we have for users to invest in themselves. And this is great for users. It's a great way for them to build equity in their avatar and feel more connected in social experience. But also for developers, because it creates some really compelling reward loops, like how you could unlock an item that makes you want to return to the game. So today we're going to talk first about Oculus Avatars and some of the progress we've made in the last 12 months. And then we'll take an in-depth look at what's coming with the expressive avatar system that we just announced in the keynote. And finally, we'll do a bit of a preview of what we're working on next. Not quite as far-thinking as Michael Abrash is. I don't have his powers of future vision, but I can tell you more or less what we think are the challenges ahead of our team. So first, I'm going to walk through the updates that we shipped for avatars on the run up to Oculus Connect 5. We made quite a few changes to the system in the last year, and I'm just going to walk through each one of them. First up, cross-platform support. So we created Oculus Avatars as an SDK so that it would be very easy for developers to drop into experiences, minimizing the cost of creating avatar asset content and also the cost of building those networked models. Initially, though, our avatars were only available for Oculus hardware, and we heard a lot of feedback from developers that they wanted to ship their apps to Oculus and beyond. So having our system restricted to just Oculus meant they basically had to reinvent the wheel and create a whole other avatar system in order to ship to 2 places, and it was hard to get avatars from 2 different avatar systems to interact with one another. So we've heard the feedback. Earlier this year, we made avatars support cross-platform. We wanted to be able to bring people together across communities, regardless of hardware, and help people build once and ship everywhere. So what we've done is updated our license to decouple the SDK from needing Oculus hardware, and also updated the SDK itself to decouple it from the Oculus runtime. This means that you can now render an avatar regardless of the hardware. You're able to query for an Oculus user and get their personalized avatar. But as of yet, we don't have an editor that would let someone who's not an Oculus user create a custom avatar. So we've created a bunch of sample avatars that anyone who's providing someone who's not an Oculus user can have something to choose from as they go into an experience. And we're looking at ways to make lightweight in-app editing, like changing the t-shirt that your avatar's wearing in a golf game or something like that. So next up, earlier this year, we did the visual update to the avatar system. If you were with us back at Oculus Connect 3, you probably can't have helped but noticed our avatars have changed a little bit since we first shipped them. Something we heard from developers was that the sci-fi style we initially went for was a little bit too opinionated and didn't always work across the different contexts of the virtual experience you were trying to build. And we also did a lot of experimentation with users, even trying out things like toon-shaded avatars to see what would resonate with people, both in terms of aesthetically pleasing, but also giving people a compelling sense of social presence. We saw that while the original sci-fi look appealed to some people, there was an overwhelming demand for people to be able to invest in and identify with the avatar they wanted to create. They wanted skin and hair color, they wanted clothing that they could recognize, and those types of things. So we updated our avatars earlier this year to use a more standard color palette. And we've heard from many developers who've integrated it since then that it just dropped much more naturally into their game without feeling out of place. And we've also updated the art and the shaders to bring them more in line with a standard physically based renderer like you'd see in Unity. This means that you can have material properties or material-like properties on clothing items and glasses. Aside from making our avatars way more easy to personalize, this is also great for things like developer items. And it's opened up a lot of area for exploration in terms of things like branding and having IP that's more recognizable on the avatar versus when it was a monochrome kind of sci-fi avatar. So whether that's a free branded t-shirt with your app's name on it, or the suit of armor that they get when they hit level 10 in the experience, this really adds a lot more flexibility to the system. And we've been iterating on this for a while now. Oculus Venues is going to be the first app to trigger unlocked avatar content, including these NBA swag, which we think look really awesome. We're using the same system to give attendees of Oculus Connect 5 free virtual avatar swag as well. So as a result of being here, you have some limited edition OC5 t-shirts and some VR League t-shirts as well, because we have the finals here tonight. So if you haven't planned to already, you should actually check out the talk after this one, where Brandon, Nancy, and Lizzie are going to talk a bit more about custom developer items and some of the interfaces that we're making available to ingest items and host them, including things for your Oculus Home on Rift. Finally, we've landed a number of performance improvements to our system. So you've hopefully all seen Oculus Venues by now. If you haven't, it's a virtual environment that can have up to 200 avatars, over 200 avatars in the same space at one time. And a lot of that was proprietary work on our part to make sure that we could interface with so many avatars and load them in all at the same time. But a number of those things have bled back into the SDK to what we ship for developers. I'm going to walk through a few of the changes we've made at that level. So first, there's our level of detail system. This enables us to load different fidelity meshes and textures for different use cases. So right now, there are 3 levels of detail. The first is the high level of detail. That's what you'd normally see on the PC avatar. In the middle is the mid-level of detail, which is more what you'd see on Oculus Go. And then low is really the level of detail for distant avatars, where you want to give some sense of body shape and maybe skin tone and color and accessories, but without needing to render in so much detail because they're so far away. In terms of how much size these things take up, the high level of detail runs at about 10,000 verts, and the mid is 25% of that. The low is a further 20% reduction. So the lowest LOD is actually only 500 verts versus Rift. And the textures go down by about 25%, and then an additional 25% again as you go down through the LODs. So the lowest level of detail is very, very lightweight and can just be used to populate areas in an app without necessarily taking up too much compute. With the addition of normal maps, we're able to bake the high level of detail fidelity down into the low levels below. So if you look here, the high and the mid are almost indistinguishable, and that's all achieved via normal maps, which we've baked from high level down. And this is really great because it means you can capture more like Rift level quality for Oculus Go and at a much better performance profile. Then there's mesh combining. So previously, avatars were rendered as multiple different mesh components, but now we're able to do that in a single draw call as a function of mesh combining, which all happens at the SDK level. We'd previously shipped this as an update for just Unity, but now it's rolled out across the entire SDK, including Unreal Engine. And then finally, there are some of the changes we made in terms of avatar loading. So we wanted to make loading and cache management of the assets we were streaming down from the web more optimized, so that it speeds up download times and how you load avatars into your scene. And one thing we've done is pipelined the way that we load assets, meaning you could load the meshes first because they're very lightweight and they normally come in pretty quickly, and then fill the textures later on. So this means that you get some sense of the presence of a person in your scene while their avatar is loading, and they can begin interacting with you in the scene, even if their textures haven't fully streamed yet, and then they can pop in as they get loaded. The one final thing we did add was what we called Simple Shader. Simple Shader is a single light source shader, which gives you a very, very good quality avatar, but without some of the complexity of tying in a full physics-based lighting model into your avatar scene. This is great for mobile compute, and it's also great for less complicated scenes where you just want to drop in avatars without having their clothing and materials responding to multiple light sources in a more complex scene. Oculus Rooms actually achieves a really best-in-class implementation of this. The single light source is configurable, so you could tie in things like day and night lighting, or even the color and intensity of what you're looking at on a TV screen. And they do all of this in Oculus Rooms, and it really sets the avatar into the scene in a way that feels quite immersive. You can see here there's also great things like reflection maps built into the Simple Shader, and so that you can really add a lot of environmental context to the avatar as it's rendered. So that brings us up to speed. We've traveled quite a long way since shipping the original Avatars SDK, and today in the keynote, we announced the more expressive avatar system that's coming later this year. Now, Will Steptoe helped me do part one of this talk at OC3, and he was sadly unable to make it today. They finally decided that having two Brits on stage presented a huge PR risk, and that no one would understand a word we were saying. But I managed to squeeze him in his digital form.
Hi everyone, this is Will from the Oculus Avatars team, and I'm delighted to present our newest expressive avatar system. We've updated the avatars with realistic eye behavior and appearance, rich lip sync, and a facial performance system that manages blinking and micro-expressions. This makes the avatar feel really dynamic, more believable, and meaningfully improves social presence.
So the fun part about making that video was that we didn't know where this was going to be at the time that we shot it, so we had no idea whether the audience would be at the same level or below. So that's why his eyes occasionally looked down, because we had to try and figure out where you'd all be sat. Before we started on this journey, I'd always been really aware of how much creating a good avatar system involved an awful lot of art effort. You have to create all of the assets and the sculpts and the style and refine it. With expressive avatars and this update, we really had to learn a lot more about the science of avatars, and particularly behavioral science. It's played a lot in getting us to a place where we feel like you can have a really good, comfortable conversation with an avatar in a shared virtual space in a way that feels very much more real than we could achieve before. So I'm going to unpack some of the video you've just seen and really talk to the art and the science of how we're working towards better social presence. So let's start with the behaviors, the science. In general, we've been quite deliberate about where we add behavioral fidelity to the avatars, as well as the performance cost of doing a lot of processing for some of these things. It's really important, we found, to have a good balance across appearance, movement, and expression, and it's fundamental to the believability of the avatar. This has been made exceptionally challenging, of course, because right now we only have very little data about what the person's doing. We know where their hands and their head are, and we know what's coming into their microphone as audio. So today I'll talk first about the improvements we made to facial behaviors and performances, and break this down into a few different components of the face. So there's the speech, how we're driving richer mouth movement with lip sync technology. There are the eyes, how we're working on making the avatars feel more connected to each other and the general experience. Then there are micro-expressions. These are the nuances that we add to an avatar to make the performance feel more dynamic and expressive, even if they're not talking. And finally, how we wrap all of this together with a controller that is responsible for managing what's in the scene, networking, and making sure everything performs as it's expected. So So let's start with speech. We had to think really carefully about the mouth and how to make speech more compelling. There were three components to our approach. So there's the avatar topology, which is the structure of the avatar and the shape of mouth movement, the way we process audio to derive this mouth movement, and then the system we developed on top of the raw signal to make animating between the different shapes of the mouth feel more natural. The first part of this then is sculptural. You'd think the sculpting of the avatar should come in the art section of my talk. But actually a lot of these revisions came from what we wanted to achieve with behavior and involved a lot of iterations as we tried to figure out how expressive and how lifelike the movement we could get on the mouth would be. Here you can see the topology for the face of our highest LOD avatar, the neutral, kind of unsculpted into any shape's form. And designing this topology that would require maximum expression also came hand in hand with making sure that that topology would enable us to have all of the different forms of body shape and structure that you'd try and encapsulate in the face, and have both of those things work together really well. So if you look at the topology, there's a lot of added detail in specific areas, like the nasolabial fold, which is this curve that goes around here, because as people's face shape changes into different forms, those areas are the places where you want to make sure you can always encapsulate the hint of a smile or a dimple or something like that. And so what we ended up doing was to take a lot of 3D scans of people's heads that they'd come in and taken of their faces, and then build out stress tests against some really, really pronounced bone structures and different levels of age to really make sure that we were flexing the right parts of the topology in accordance with both how they wanted to express what they looked like and also how the avatars would be expressive on top of that. So the base mesh we arrived at that powers all the avatars can accommodate a really wide variety of structure, but on top of which our expressions ride really nicely. So we put a lot of work into then getting the shape of the mouth as you form different sounds to feel really good. Here's Will in slow motion. He's obviously muted right now, otherwise it would sound really weird. We wanted to get the most out of the mouth movement with the raw signal that we have available from the microphone. And we spent a lot of time tweaking the mouth movement and accentuating certain shapes, and worked with face movement tracking experts and linguists to perfect this approach. So to give you an example of the kind of level of analysis we did here, this is the International Phonetic Alphabet. I'm assuming most people can't read this, but people who can are able to more or less pronounce any word in any language in a way that the receiver, if they are from that country, would perceive that they were pronouncing it the right way. I've always been told that my pronunciation of French is awful. This, in part, helped me explain why. There are certain sounds here I don't know how to make that are used in French. And that's a really interesting nuance to how people pronounce and make different shapes with their mouths. Very few people can make all of these sounds. And in fact, I was one of the only people on our team who can do what's called a uvular fricative. Something to brag about. So it's really interesting because linguists have effectively codified how we make sound into charts which explain the mechanics of making sound. A great example is vowels. Vowels are really just made by the extent to which you open your mouth and where the sound is formed from the front to the back of your throat. And so all of the vowel sounds you can think of making are encapsulated in this chart, and it is literally broken out by front, back, and mouth open and closed. Now everyone in the audience is silently going, yeah, ooh, to try and make those sounds. I can see 4 of you doing it. Are there any parents in the room? Show of hands? Okay. So it's really interesting, but I was kind of jealous that my son said mama before dada. It turns out this chart put my mind at ease. The da sound in dada is what's called a dental sound. You can't make it until you've learned to bounce the tip of your tongue off the back of your teeth and top of your mouth. You need teeth to say dada properly. So apart from telling me all of the different words that I should try and teach my son to say next, these charts also gave us a really good understanding of where we could collapse the problem set of trying to refine and accentuate speech. For example, making plosive sounds, which are where you exhale quickly to make the sound, like a p or b sound, requires making the sound in shape before the sound is heard. The air coming out of your mouth is actually what makes the sound that you hear, but there's a lot of shape that happens before it. And in networked simulation, without adding a lot of latency, we had to resort to accentuating some of the shapes that you use when you make a plosive sound so that it would read like a p or b, even though you might get the sound and the shape at slightly different times. At the other end of the spectrum, things like ta and da look indistinguishable from the outside. You literally can't tell if you're looking at someone very easily whether they are making either one of those two sounds. And so we were able to collapse the problem set of how many different expressions and ways we could analyze audio to figure out those different sounds was down to a smaller subset. So we were able to be more efficient with our performance. These updates to the structure and then the animation blend shapes went hand in hand with how we process audio in the first place. So we recently updated our audio SDK with a greatly improved lip sync function based on a lot of machine learning. We literally worked with hundreds of people who came in and recorded themselves talking with video, capturing what they were doing, tagged it by hand to figure out exactly what shapes they made when they were making different sounds. And this allows us to deliver much more rich and accurate animations up to the system. One of the great things about these SDKs being worked on hand in hand as we're developing hardware is also that we're able to move some of these things over to the dedicated DSPs on our hardware, and that's obviously really advantageous for any developer. If you want to find out more specifically about lip sync, Elif is doing a classroom talk on lip sync, and you should definitely check it out. It's really great stuff. So before we go any further, I'm going to use the term viseme a lot. A viseme is a visualization of the shape of your mouth as it makes a different sound. So here are 3 examples of that, and they're kind of important to everything that happens next. So the vanilla lip sync SDK serves a set of suggested visemes from the input audio with a varying level of probability that you're making each viseme. And how you use this information is really flexible. It's great because the way that you use this information really is ultimately informed by the avatar style you're trying to achieve. We wanted to create very, very bold, clear, and readable shapes on a more human, realistic form. And so we end up filtering the visemes to just the strongest predictors of what you're saying. Basically, this means that most of the time, we believe that you are saying a single viseme most of the time instead of suggesting multiples. And what we found was that with more realistic forms, this removed some of the noise from the face where the other suggested visemes might be creeping in. So we have the shapes and we have the signal. Now we just need to animate them, put it all together. One of the main issues with taking a set of visemes and directly applying it to an avatar is that without doing anything more creative, it can sometimes seem flappy or choppy. And it's because of a few different characteristics. One is that in the gaps between speech, when the mouth goes from making an accentuated shape back to neutral, you suddenly move your mouth much more rapidly than you could possibly move your mouth in real life. That gives you that sense of flappiness. And the other example is that when you go from 2 more extreme shapes, you suddenly see the mouth contort in a way that you know is not physically possible. So using the example of saying hello here, you could imagine the mouth animating between 4 distinct shapes to make the sounds that say hello. And this is an example. This is a very simplified example of what you would get from the lip sync SDK once we filtered out the other visemes. One approach, and something that's built into the SDK, is blending and smoothing the visemes across them to give you more of a sense that one is tailing off as the other one is coming in. And this is really great, depending on the avatar style, particularly in more abstract styles. Smoothing is a great way to reduce that flappy mouth effect. We found that as we push for more realistic avatars, smoothing as a concept didn't quite work for us. And it makes sense. If you think about someone's face moving, you rarely use the word smooth to describe the shape of someone's lips. So we had to come up with a more accurate model for how the mouth moves as you talk. We nicknamed this the physically based blender, kind of like how you have a physically based shader for textures and materials. If we examine each one of these visemes, it's actually a composite of facial muscle groups. So you have things like jaw drop and cheek puller and dimpler. These are all individual muscle triggered actions, and action units is the formal terminology for these. Some of them are contracting, some of them are relaxing, and they're all doing it to different intensities and at different speeds. That's why when you see a mouth actually talking, it's rarely just moving between different states. And it's more of a turmoil of all of these different muscles pulling in different ways. So what we did was simulate the strength and animation into and out of different action units across the visemes, and this results in a much more natural mouth movement. It makes the face feel more dynamic as well, because depending on how quickly you speak, you normally only make partial shapes in some circumstances. So the model takes account of the fact that you couldn't possibly get from one shape to another, and you might go half of the way there before you're now into the next viseme. This gives the face a sense of dynamism and also makes it feel like you're never really seeing the same shape on someone's lips at the same time. It makes it a lot more responsive. It also gets rid of some of the artifacts you see from things like the mouth returning to a neutral state, because the muscles actually relax independently at different speeds as you go back to the base state. So it's quite hard to see this in video, but I've got a few different avatars side by side. And on the left we have, we have the raw signal, and on all the way to the right we have what we're thinking of as an increasingly physically based blend. The things I'd call out are, when you see the speech stopping, the way that the mouth moves back to neutral on the left-hand side is quite quick and jarring without any animation to smooth it. Whereas on the right-hand side, you see a much more subtle relaxing of the tension in the mouth. This is a really, really granular nuance of facial animation, but what we found was that with this on and off, if you spent long periods of time talking to someone, having it switched on was actually the difference between feeling like their face didn't feel like a genuine face performance versus having it there. And so it's a really, really subtle nuance of face performance. The other place you can see it, which is quite hard to catch, is when the mouth quickly moves between extremes of different shapes. And there are a few places in this video where that happens. And you can see on the right-hand side, the mouth just suddenly jars a bit up and down as it goes into those shapes. Whereas on the physically based blend, it's a lot more smooth, and you see different muscles pulling in different ways. This is obviously specific to avatar style. So, you know, the raw signal is actually perfect depending on whether you have a more abstract form, or even in the case of people who are using textures for the mouth shape, then it makes a lot more sense to use bold, clean images for the texture in a 2D mouth avatar. But as we went more towards realism, we really found that we needed this level of natural movement for the mouth to feel really great to interact with for long periods of time. Let's talk about the eyes. Apparently, they are the window to your VR soul. So working on avatars, as you might have guessed, has taught me more about the way our body works than any class I ever took at school. And it turns out that our eyes and the associated movements around them are incredibly well understood and even predictable. We're hardwired to do certain things, and there are decades of academic study on how humans behave in social circumstances that we were able to reference when encoding more compelling eye behaviors. Most of the time, for example, you blink without thinking about it. Blinking is a function of your eyeball moving, parts of it drying out, and your eyelid washes over your eyeball to keep it from drying out. It turns out if you're looking around a room and you look very quickly in multiple different directions, you have a higher likelihood of blinking twice in a row. People also tend to blink at the end of sentences when they come to a stop. These things are very much in the realm of automatic, and so we're able to simulate some of these happening with a higher degree of confidence than we might anything else. In terms of eye movement, there are 3 characteristic profiles of how the eyes move that we were able to encapsulate into the SDK. The first is the way that our eyes make sudden movements as we change focus completely. So as I look from the left side of the room to the right side of the room, my eye is performing what's called a saccade. And a saccade is essentially a ballistic motion as your eye rotates around very quickly and stops in place where you want to look. And it has a very well understood dynamic profile that we were able to model. This is very different from what we do when we're tracking an object as it moves across the room. This is called a smooth pursuit. And smooth pursuits, as you track an object out of your vision, cause the eye to move in a certain way. Saccades and smooth pursuits working together as you both change your focus and also as your focus tracks for you really need to be refined to make sure that they feel like they're working in cohesion. Finally, on top of this, we have microsaccades, which are the tiny or fixation movements that you make. And this is when your eye is changing where the image lands on the back of your retina. They're very subtle micro movements that when your eye settles in place, you see this little wobble. And actually, we found out that in video that we captured, we couldn't show it because it doesn't show up at 30 frames. But at 90 frames per second in VR, you really do notice it. The way that the eye comes to a stop feels much better. So these have all been built into our eye system. One of the reasons eye models sometimes run into the uncanny zone is that the eyes go beyond what we expect in terms of the natural range of motion. So making eye contact with someone where the avatar is to the right of you and they look up and your eyes are pointing directly into the kind of far right of their eye socket. This is actually really uncomfortable to do. I would challenge anyone in this room to try and look at the person to their right without feeling a bit of pain, without moving their head. It's not something you want to do for a long period of time, and it does feel weird when you see someone else doing it. So we factored this into how we do eye targeting. Within your field of view, it turns out your eyes have a horizontal and vertical comfort zone, outside of which you don't normally hold a gaze for long periods of time. You might start looking at an object in the sweet spot of what's more directly in front of you and then track it outside of the comfort zone, but you won't typically make eye contact with something that's right outside of your periphery. You typically turn your head when you're going to make eye contact with something that's in your periphery. The constraints of the VR headset actually really help us here. Our field of view is reduced. It's narrowed beyond the periphery of the eye. And the sweet spot of focal clarity means that really, for the most part, your head is tilting and you are looking in the direction, more or less, of the thing you're trying to look at. If you're in a social VR situation and there is an avatar looking at you out of the corner of their eye, I can say with quite a lot of confidence, there is no way that the person is actually doing that right now, because they would be looking at the walls of their lens. And that's not fun for anyone. We observed this really early on with Avatars 1.0 in research, and we saw that the nose bridge was actually incredibly indicative of the eye gaze direction with some tolerance. Because the field of view is more limited, people tend to turn their heads more when they're trying to make eye contact or look at someone. And that level of the social norm of attention focus when you're in things like a virtual meeting, we found that even without eye models, just seeing the nose bridge gave people a great sense of attention where people were focusing. So we take the items in the scene within this reduced comfort field of view, and we give them a salience score. A salience score really can be an estimator of how likely you are to be looking at that object at a given time. If it's just an object in the scene, it might be quite low. If it's another avatar, you'd expect it to be higher, even higher if they are talking. And you can imagine things like if one avatar is using their finger-based pointer, then the point of destination of what they're gazing at is very likely an indicator of what they're looking at that given moment in time as they traverse UI. This model is really customizable and parameterizable, so you could assign it to a TV screen in the scene or any other object that you think might be of interest. And it's run less frequently than what you think of as the per-frame animations of moving the hands, etc., because you don't really tend to refocus your eyes 90 times a second. This gives us a really natural way to model the animation of eye movement without overloading and trying to do too much every single frame. And also enables us to pass essentially new gaze targets into the system to animate with those smooth pursuits and those larger saccadic movements in a way that feels really great. As the head tilts around, you can see new objects are coming into Will's perspective on the avatar behind me. And that's an example of where the salience of a new object is being calculated, the eye model adjusts, and then he's actually doing a smooth pursuit as his head continues to move while he's tracking the old object. One thing we do specific to avatars and faces is put a few different targets on the face of an avatar, because for most people, when you're holding a conversation with someone, you look at their face, but your eyes adjust around the face as you're talking to them. So having a few different gaze targets enables us to simulate this effect. Then there are the behaviors of the eyes themselves, and they're also quite parameterizable. So you can see here on a close-up, there's a customizable reflection map that you can dial in to the eyes and control the glint on the eye as well. It's also actually possible to dial in dilations. We realized that as the light intensity of the scene changed, having eye dilation was a really, really important thing in low-level scenes. It's just something you expect to see when you're looking at someone in the eyes. And it can be wired into things like, as an avatar jumps into the scene for the first time, your eyes dilate slightly as you see them, which is what we do when we see other people for the first time. Finally, something we've been really conscious of is accounting for latency and performance. It generally doesn't bode well if you calculate the eye gaze for every avatar on every computer. It's very inefficient, but it also leads to occasions where two people might think the same person is looking at them, and that can be socially awkward. So it's good to have some level of authoritative calculation of where the eye is looking. Once we've calculated a gaze target, we pass an identifier for the target over the network. And this solves for a few different things. One, it means that me, the client, is always figuring out where they look and distributing it. But it also means we're not passing every frame what I am looking at. We're passing as the gaze changes identifier over the network, meaning that on the recipient end, we're able to animate the ballistic profiles and things without worrying about a dropped frame causing the eye to suddenly jerk in a really unnatural way. So eyes, mouth, what about the rest? Part of making a more expressive avatar system is focusing on the expressions and the nuances that you'd expect to see when someone isn't talking, when there's no signal whatsoever. And this is really challenging. We don't have a face-tracked camera. There's no way to see what you're doing with your face. But there are known things that we can infer about what someone's face might be doing with more predictable accuracy. And then there are also things that your face does kind of in the background while it's idling that have been observed and can be encapsulated into the avatar behaviors. So some of these are very easy. There's lots of research about how your brow works in general. Other than for things like shock and surprise, your brow generally tends to move in line with things like certain mouth shapes, and also just as you tilt your head, you generally lift your brows up so that they don't get in the way of your eyes, especially if you have really big, bushy eyebrows. Beyond this, though, we wanted to create a more dynamic performance by avoiding this contrast between speaking and not speaking. And so we tried to get around the fact that our faces really rarely remain motionless. We had to avoid things like overt expression when we were thinking about this, to make sure we didn't stray into implying mood, because we're simulating everything we're doing here, and it wouldn't be great if we suddenly decided your avatar was angry in a social, at a party, let's say. It turns out just a hint of the wrong eyebrow shape can cause people to stand slightly further away from one another, while having a slight blush on the cheeks can make them stand closer. So these are things that people really respond to. A very subtle smile dialed in correctly can add a lot of warmth, but there's a lot of risk if you use something like disgust, which is an almost universal negative facial expression in any culture. So we experimented a lot with a set of smaller, more subtle movements to drive what we call ambient liveliness. These are both triggered and random, because we have some events that predict these, and blend into the face to give it a sense of human behavior, or more human dynamism. And here we're just showing the rest state mouth movement variations, so the very subtle ways that your face might move while you're not talking at all. It's a really good thing that video is really big, because this is really subtle and hard to see. But if you look around Will's jaw and lips, there's a slight pursing of the lips, there's a slight movement of the jaw that, without it, a face can feel very, very still as a baseline, but just adding these subtle things makes it feel like the person is there and driving it, which is really interesting. We also have some asymmetries, nothing this extreme, but we're rarely a perfect mirror image. And slight asymmetries in base pose, variations in the symmetry of the brow and the lip shape as you talk, all fold into making an avatar that doesn't feel like it's just repeating a set of motions over and over again as it's talking. It gives it a lot more nuance. So tying all this together is what we think of as the expression controller. This does some really neat stuff, like only querying for the Visime data for avatars that are in a given frame, managing the hierarchy of inputs so that there are overriding things you'll always do, like blink, and making sure they're always triggered in the right way so that blinking always feels natural. It's also quite a modular interface. So as new forms of tracking come online, as new heuristics come online, we'll be able to wire them in over time and add more expressivity and dynamism to the avatar. And it handles the networking and performance management of the system as well, making sure we're not doing too much at any one given moment in time. So we talked about the science. Now we can talk about the art. Evolving the art style took quite a lot of experimentation. One of the hardest things we found was creating a more realistic avatar in maintaining the balance between the fidelity of the avatar as a whole. So if you add photorealistic skin, but then you fail to make it stretch and wrinkle exactly like skin, you typically head in the direction of uncanny valley. As we planned for more expressive avatars 12 months ago, we had to consider the art style against the introduction of all this new behavioral magic. And this is the reason that we came up with the Will avatar that we saw a year ago, which looks nothing like Will. But we demoed at Oculus Connect 4. So we established the parameters of behavior pretty early on, allowing us to inform the art style and see if we would change anything drastically to get to where we wanted to go. The first thing we did was look at the gamut of movies and video games and come up with something of a spectrum across more abstract to realism in avatar art. And what we realized was that sculptural fidelity, the 3D topology of meshes, was typically the setting standard for how real or abstract that avatar could look. But the textures and shaders could provide you some modification. You could take an ultra-real avatar and make it look more cartoony, but you can't take a cartoon sculpted avatar and make it look more like a realistic human. And we did some stress tests here. So this is some of the experimentation we did on form and proportions using our rig. And what we found was that there was a strange moment, and we realized that the more abstracted style of the avatar, suddenly we didn't care as much about all of the human behaviors it had. It was as if the fact that it was abstract made us go, okay, I can disregard this trying to be a human. And it's a very good mechanism of opting out of having to tackle some of the hard challenges of human behavior. But we really wanted to try and get to somewhere that felt more human because it raises the expectation of human behavior, and we feel like that's actually important in fostering, deep and meaningful connections in VR. What's interesting is that we do this all the time with movie characters in animated films. And it's not a problem. You can, fall in love with an animated character regardless of its shape and form. And animators are able to accentuate some of those things because they know what someone's thinking, and they know what the performance is supposed to be doing, and so they can really go into making expressions come to life. But when you're talking about a tracked, moving human in a scene where you have very, very realistic and high-quality motion, but then you don't match it with what feels like realism in the form, there's an element of jarring nature to that, and we were trying to avoid it. So with more of an opinion on form and trying to head towards realism, we actually did some experiments on textures and shaders to understand that gamut. Here we have the same avatar head rendered with a very soft texture which plays down skin-like properties, and an ultra-real one which has things like detail down to the pore level in the normal maps. And we found that the detailed pore lines made us expect to see things like wrinkles and skin stretching, and those are expectations you really can't reasonably meet within the level of compute that we're trying to establish for the avatars. You'll also note both of these guys are bald. And that's because increasing the realism of skin gave us wildly unrealistic expectations of what hair should do across all the different types of hair that exist. You're talking about strand modeling and all of the physics you see in top-end AAA games, and getting those things to work across our gamut of device and performance specs would be really, really hard to do consistently. It's also just hard to make it feel completely real when it's being driven by human motion. Ultimately, we went for a balance between form and rendering that leans towards sculptural realism, but uses textures and rendering to actually pull it back away from something that would look too photorealistic to match where we thought we could get with behavioral realism. After all, we are only simulating the things that you're doing, and we can't possibly know that you are performing a real smile, for example, in VR at this point. This final look's actually achieved through a few different things. So we have rim lighting, which you can see is the kind of outline around the avatar in the profile. This is really important in showing and highlighting gaze direction and where someone's attention might be, because it highlights the form of the avatar more richly against the backdrop. And it's actually really effective when it's turned on. You can tell where someone's nose bridge is pointing without even looking at their eyes. So the other thing we did was reduce what we called wear and tear. These are things like blemishes and wrinkles and fine lines, because they really play up the expectation that this is going to behave like real skin. If you see wrinkles, you expect them to move like wrinkles. And we also, in general, softened features across the palette of the face. So the skin, if you look at this map, flattened is a much more smooth skin, and that gives us a softer shade for the avatar, which feels less like real skin. We also simplified things like brows and lashes. That comment on hair realism features into how we thought about the eyebrows and the lashes. Obviously, modeling those as real hair strands that would move as your eyebrow raised isn't something we wanted to try and do with this generation of the avatars, and so they're more simple, bold shapes. And finally, we have the improved eye shader we talked about earlier, so adding things like reflection, making the eyes feel more part of the scene as part of the style overhaul. So the choices we made in behavior and style allow us to create a system that would work well to deliver these expressive avatars across both PC and mobile. So here we have a sample of Rift and mobile quality avatars, and they're really hard to tell apart. And I think we're pretty happy with having got to that stage. They're obviously doing simulated head motion, so it's a bit like you're hanging out with 6 of the Borg. But you can hopefully see that there's not a lot of differences in terms of the mesh fidelity, the hair quality, and the way that the face is expressing and the eyes are moving as they go through that cycle. So that wraps up the current state of avatar social presence, and hopefully you've got a sense about how we're thinking about social presence and the work that's going into delivering these avatars in a way that feels more comfortable, dynamic, and expressive. Finally, I want to quickly talk about what's coming down the road. We wanted to provide developers with rich social presence, leveraging state-of-the-art technology. And for users, we want to enable rich customization. There are some obvious areas we're continuing to focus, and we're definitely excited about doing more in the area of cross-platform, making it so that you can take your avatar really anywhere. So we'll continue to add samples and do work here. There are also the new inputs and behaviors that will come online as we advance the state of the art. So obviously we have Oculus Quest, and making sure that its hardware works seamlessly with the avatar experience. But you've also got things like new additions to the lip sync model that we'll be bringing into the avatar performance over time. We're most excited about bringing more to the avatar form, driving towards full body presence. I mentioned before about raising the bar of overall avatar performance and doing this equally across features and behaviors. And this full body presence really poses a lot of challenges that we're excited to solve. To give you an example, understanding what someone is doing in the real world versus what their avatar is doing and making that feel like a very comfortable experience. If they are seated but their avatar is standing or vice versa, is one challenge in making sure that the movement feels right, because you do move differently when you're seated versus when you're standing. How we balance between the hybrid tracking and simulation is also very interesting. If you think about locomotion of the legs while you're sitting without moving your arms, the avatar will look very strange as it traverses the space in front of someone. And so there are some great challenges here. And then there are body size differences. How do we account for the shape that you want to be and the shape that you are in a way that both feels good, looks good, and also works with all of the input parameters? If you're giving yourself an avatar that's 10 feet tall, how are you going to make sure that you can shake hands with someone else in VR in a way that is comfortable and obvious to both parties? And finally, then, there's matching behavioral realism across the avatar form. If you think about something like the facial behavior system, we're striving more and more towards realism. And that puts a lot of stress on us having to have clothing that also behaves in a very realistic way. So you can expect us to talk more about our learnings as we've progressed in these areas, but these are some of the challenges ahead in our work towards full-body avatars. Here's just a sense of the kind of work we're doing. So this is a preview of some of the IK system improvements we've been making to the torso of the avatar, to the point that actually you can use it comfortably in the first person, and the wrist behaves very well. And it's just using the same tracked hands that we already have today. So I filmed my colleague Barrett here, but all we're using for the input is just the hands and the head, not using a camera input to drive the body or anything like that. And you can see that the shoulders, the clavicle rotation, the hips are moving in a way that actually conforms quite well to what he's doing in real life. Finally, as we continue to build up our content ecosystem and the specification for all these rigs, we're really excited about opening this toolchain out to any developer to use for any type of avatar that could be piloted by the same system for narrative characters or NPCs. So here are a couple of stress tests just to show you that we're not all serious on the team. We're building this in such a way that you could imagine giving us a derivative from that base mesh, and we would be able to populate all of the levels of detail and all of the expressions in a way that ride comfortably on top of that base derivative. So combining this with the parameters and the behavior system, which are also configurable by a developer, you could imagine people taking this and creating really charismatic and expressive avatars in a particular character or style for something like an NPC in a way that feels really great. That's all from me. Stay tuned for more updates on the Avatars SDK. We'll continue to use the developer forum and blogs to announce the coming updates to our system, and we love hearing your feedback. We really do. We don't have time for an official Q&A, but myself and Steve from the team will be outside if anyone has any questions for us. Thank you.